Hello. Today we're going to look at the converse of Pythagoras' theorem. Well, it's written out here in a bunch of words, but none of that really means much. The important part's right here. If this holds, if this side, get down to it, if any particular side of a triangle is equal to the sum of the squares of the other two sides, then you have a right triangle. It's pretty simple, really. Pythagoras' theorem just says that if this is a right triangle, then a squared plus b squared equals c squared. Now the converse simply says that we're not sure if this is a right triangle, but if a squared plus b squared equals c squared, then it is definitely a right triangle. Now that can be used. It's a practical thing to know. Let's see if I can give myself a little bit more room here. If you ever want to build anything, even a little shack or extend a deck out from your house, add a garage, you're probably going to want right angles. Things don't look right if you just use sloppy angles when you put things together. On top of which, when you get to the end, the two sides may not match up. You may end up with one side that looks like that and the other side comes in like that. Oops. They're supposed to be together and they're not supposed to be like that. Well, when you need to get your angles right, that is to say you need right angles, there's an easy way to do that. In fact, there are some guys into construction who just routinely carry 3 stakes, string, and a tape measure, and that's all you need to set up a right angle of virtually any size, really. Well, I suppose there are limits to that, but one thing you want to do is remember your 3, 4, 5 triple. That means if you want a big one, you can make it 30, 40, 50. Let's suppose you use the 3, 4, 5. Well, what you do is you just lay out stakes. You put one here, you put one here, and you put one here. Now you measure this, and you run a string from here to here. And this is 3 feet. Now you put another stake here and make sure it's exactly 4 feet, and run your string here. Now you've attached string here to each of these so that when you move a stake, you can't change the distance from one stake to the other because it's tethered by the string. So now what you do is you measure this distance right here. And suppose this turns out to be 5 feet 2 inches. Well, that's too long. So this stake, which is tethered by a string to this stake, you move this way a little bit. And then you measure. And maybe this time it's 4 feet 11 inches. Well, okay, you move it back out a little bit. When this gets to be exactly 5 feet, you drive the stake, anchor everything down, and now this part here will be a right angle. There's no way around it. It's actually a pretty easy way to make a right angle. And then what you do is you got a piece of string here, right? You just tie some string to this stake. You extend the string off as far as you want out to here, making sure that the string touches the side of this stake, the side of this stake, and you just keep it straight, maintain tension, and then you do the same thing out here with the string touching this side of the stake and this side, and you extend it out. And now you have something that may be, say, 20 feet by 10 feet, good sized shed, and it'll be perfect right angles. And you can do that all the way around, do it here, and over here in 4 different places. Now you've got 4 right angles all set up, and the stuff you build will look like a professional did it, instead of looking like I did it. And there's a couple of quick, simple facts that also relate the sum of the squares to the third side, or pardon me, the square of the third side. If you take the longest side of a triangle, we'll looks like that'll be C in this particular triangle. If it's less than the sum of the squares of the other two sides, then you have an acute triangle. If not, if it's greater, then you have an obtuse triangle. And we just figured out a couple of seconds ago that if this is an equality, then you have a right triangle. And I believe the sense of this is probably fairly easy. And if this were a right triangle, then we'd have a straight line dropped down here. And C would be just a little bit longer, wouldn't it? And it would be equal to a squared plus b squared. By reducing the size of this angle, we've shortened what used to be the hypotenuse, but now it's just the opposite side of what used to be the right angle. We could say it that way, I guess. And same thing down here. It's we take this, which used to be a right angle, and swing it out this way. We extend the length of this. So now what used to be a right angle is much larger and producing an opposite side, which is longer. I believe you can see the sense of this pretty easily. Look at it this way. If c squared is less than a squared plus b squared, it's got to be something. It can't be a right triangle. So you got to choose between obtuse and acute. And acute just seems like the right choice. Well, now that we've got these theorems under our belt, let's do some problems. This will be a pretty easy section, really. It's kind of like Pythagoras' theorem. You've seen it before. You're somewhat familiar with it. And the converse of Pythagoras' theorem is not real earth-shattering. So are any of these Pythagorean triples? Darn, I don't see where it is. Let's see here. 3 times 5, 5 times 2. Oops, nope, that won't work. Well, shucks. That one looks too big, but who knows? I could be all wrong. This one looks like these two are too close together, but maybe I'm wrong. In fact, we just worked a problem, didn't we, in the previous section, where things worked out to be 5, 12, and 13. So, let's try it. 12 squared is 144, right? 5 squared is 25. That's 169. And that is 13 squared. So this one's okay. Yeah, this one might be easy because it's got a 10 in there, so we can square that real easy. Here we got 100 plus 24 squared. Now, after grabbing the calculator and squaring a couple of things here, I get 24 squared is 576. I put a question mark in here because I don't know what the relationship is yet. And 28 squared, well, that's 784. Well, 100 plus 576 is 676, and that's not 784. In fact, this is less than. So we have the long side is too big. They didn't ask, but what does that tell us? It's an obtuse. It's an obtuse triangle, right? Because this is larger than this squared plus this squared. So I'm pretty sure the answer is going to be B. But let's take a look at the others and see if they actually work out. Let's see, 15 squared is 225. So just to check, we went ahead and checked out C. That's 15 squared is 225, 1296 for 36 squared, and 39 squared, 1521. Well, if we add these together, remember I put these question marks in here because don't know what the relationship is until we get done. Well, this is 1521. That equals 1521. So this is a right triangle. And this here, 50 squared is 2,500. 120 squared is 14,400. 130 squared is 16,900. When we add them up, they're equal. So B was definitely the one that didn't match up. Well, for this, remember, scaling means that none of the sides have equal length. They're all different. And that certainly applies here. 4, 7, and 9 is different. But what kind of triangle do we have here? Well, we need to square these and add them up and see what happens. I get 16. 4 squared is 16, right? Plus 49. And how does that relate to 81? It doesn't look like it's going to be equal to me. So we add these up, and the relationship is that this squared plus this squared is less than 9 squared. Well, if the two sides squared add up to less than the larger side squared, that means it's obtuse, right? The other way to write this is that the big one squared, the large side squared, is larger than the sum of the squares of the other two. That means it's obtuse. And so the answer to this, of course, is C. Well, according to this, somebody told you that if you double all the sides of a right triangle, the new triangle is obtuse. Well, that's not right, but let's analyze it rather than just talk about it. In other words, if you wanted to prove to somebody that this is not true, how would you do that? I mean, without spending all day on it. That's pretty easy, really. Suppose you have, well, let's see here. Let's start with a right triangle. Here we have a right triangle, and we've got H, A, and B. Now this is a right triangle, so we know that B squared plus A squared equals H squared. Suppose we took some other triangle and made it twice as big. Maybe I can do that. Let's just pretend. Now we made this twice as big, so the sides now are 2B, 2A, and 2H. Is that going to be now a obtuse, acute, or right triangle? Well, let's try it and see what happens. Since we double everything, this is still the longer side, after all. If A is bigger than B and we double A and double B, then 2A is still bigger than 2B. So let's try it. Suppose we get 2A squared, then we got 2B, and over here, our new side, which we don't know what the relationship is yet, is 2H squared. Well, let's see here. This is just going to be 4A squared. And this is, pardon me, 4H squared. Now this is equal to, less than, or greater than. Whatever it is, if we were to multiply both sides by 1 over 4, what would we get? We get A squared plus B squared, and then A squared over here, which we already know are the proper dimensions for a right triangle. We know that from the converse of the Pythagorean Theorem. If you don't like doing it this way, you could also write this. you could use your distributive law to rewrite this whole thing as 4 times a squared plus b squared. And over here we have 4 times h squared. And we can put an equality in here, because if a squared plus b squared equals h squared, then from our multiplication property of equality, we just multiplied by 4 on each side. We still have a right triangle because the equation is still satisfied. We still have an equality here. Here's one that's tempting to oversimplify this, I think. We'll know for sure as we go through it. 6, 8, and x. Well, does this ring any bells? How about 3 times 2 and 4 times 2? So make this 5 times 2, and we've definitely got a right triangle. In other words, if x was equal to 10, we just have a multiple of our triple, our 3, 4, 5 triple. Just multiply it by 2, we get 2 times 3 is 6, 2 times 4 is 8, and 2 times 5 is 10. So 10 would make it a right triangle. On the other hand, if I'm going to put it up here because we're going to do some more calculations. For acute, then x will be less than 10, but of course greater than 0. And for obtuse, well, x is greater than 10, pardon me, greater than 10. But of course it also has to be less than the sum of these two sides, which is 14. So from 10 to 14, it's obtuse. From 0 to 10, it's acute. At 10, it's a right angle. But suppose x is not the hypotenuse. The way things are laid out, 6 could never be the hypotenuse because it's smaller than this side here. But if we chose x to be smaller than 8, then 8 might be the hypotenuse. So how do we do that? Well, in that case, we'd have 8 squared. So that's the hypotenuse, equals 6 squared plus x squared, or x squared equals, let's see, 64 minus 36, right? Oops. Yeah, that's right. So there's another value of x. It turns out, if I let the hypotenuse have length 8, then I've got 8 squared equals 6 squared plus x squared. 8 squared is 64, so I subtract the 6 squared from each side and get that x squared equals 28. So x is the square root of 4 times 7. I just broke it down that way to make it easier to take the square root of the 4 and leave the 7 as it is. So we get 2 times the square root of 7. That's another option for x. Now if we chose this one for x, that would be one of our legs. Now what would our choices be? I went ahead and drew a little picture over here for this new case where x equals 2 times the square root of 7. We've got this right triangle where the hypotenuse is 8, this leg is 6, and this leg is 2 times the square root of 7. So how would we make this acute? Remember, this is the one we get to change. So we have to have that 6 squared plus our new length. If it's less than 8, then it's going to be obtuse. With a 50-50 chance I said it wrong. Looking at it backwards, of course, as usual. The hypotenuse here, if it's bigger than the sum of these two squares, then we have an obtuse, and this is greater than 90 degrees. If the hypotenuse is less than the sum of these two squares, the square of the hypotenuse is less than the sum of these two squares, then this would have to be a smaller angle, and this would be acute. So to make this acute, we have to make this bigger. That makes this relatively smaller. That means it's greater than 2 times the square root of 7. But how big can it get? Well, don't forget that we already figured out that when x gets up to 10, we've got a right triangle. So if we expand x all the way up to 10, we've got an acute triangle right up until 10. Now we've got another right triangle, a whole other right triangle where this becomes the hypotenuse and these are the legs. And you can see where that might happen as you extend this out. This angle gets bigger and bigger until it becomes a right angle. Well, actually this will have to move in and then out, and then this will become a right angle. So if we put x between 10 and 2 times the square root of 7, this will have to be an acute angle. That makes this part, this hypotenuse, less, the square of this hypotenuse, less than the sum of these two squares. On the other hand, when x is less than 2 times the square root of 7, it's going to be obtuse. What about this limit over here? Why that? Well, that's because of the triangle inequality. These two sides have to be larger than this side. That is, the sum of these two sides have to be larger than this side. If this were to drop down less than 2, then 6 plus this would be less than this side here, and that's not allowed. Now that we've done this, we need to correct this part up here. This is okay, but what about the lower end here? If x drops down below 10, it becomes an acute triangle up until it reaches 2 times the square root of 7. And if you're wondering, that's about 5 1/4. 2 times the square root of 7 is. So this 0 here should really be 2 times the square root of 7. So our ranges here are 10 to 2 times the square root of 7, in between there. Or, that's for acute. For obtuse, it can be from 10 to 14. Or, it can drop down below 10. Well, I got it right here. Same thing. I just adjusted this so it matches up with this here. And then this one. For obtuse, it can also be between 5 1/4 and 2. So if we were to put this on a number line, maybe it'll be a little bit less confusing here. To put this in a bit more organized way, put a number line down here. The stuff up on top, this is obtuse. I put the obtuse intervals here in blue and the acute intervals down here in blue. So, and this is the point 2. So from 2 to 2 times the square root of 7, which is 5.26 roughly, from 2 to here would be obtuse. From 5.26 to 10, this range, it's acute, and then it becomes obtuse again from 10 to 14. Now on this one, they actually tell us which one is the longest side. that'll help. So what we have to do is figure out what values of x will make this quantity squared larger than the sum of these two quantities squared. First, I'm going to figure out which value of x sets these equal. In other words, which value of x gives us a right triangle, because that'll be the limit. Now, when we pull a 4 out of this, after we, well, first we obviously have to set this up, expand these two and this one, and we get all this stuff is equal to all this stuff over here. Right off the bat, we have a +1 here and a +1 here, so we just toss them both out. Subtract 1 from each side. That works okay. Now we have a 16x squared, 4x squared, that's 20x squared, and 36x squared here. So if we subtract the 20x squared from the 36x squared, we get 16x squared over here. We add the 12x to the 48x plus the 4x over here, and you get 64x, and then we've got a 36. So we've got 16 squared equals this stuff. Or we can rewrite this in our standard quadratic equation form and set it all equal to 0. And then we pull out the 4. And we get this. Now, it may be obvious to you what the factors are for this, but me, I just use the old quadratic equation. Remember? I'll write the general equation out in case we haven't used it for a long time. So, in fact, I don't think we've used it at all in this class. I'm not sure. That's b squared minus 4ac all over 2a. And this will give you x if this is a, this is b, and this is c. Remember, the standard quadratic was ax squared plus bx plus c equals 0. When you have that, you can write that x equals minus b plus or minus the square root of b squared minus 4ac all over 2a. So if we put some actual numbers in there, and by the way, we only need to solve this, because if we're setting it equal to 0, multiply through by 1/4. 1/4 times 0 is still 0. So we can just drop what we pulled out of here and solve this, and we'll be good. So b is 16. Actually, b is negative 16, and negative 16 is 16. Okay. Plus or minus, well, minus 16 squared. And I'll just write it as minus 16 squared for now. Minus 4 times a, which is 4. C is minus 9. So we're going to have a minus 9 and a negative sign here, so the whole thing is going to end up, and I should have put the parentheses around. There we go. So this negative sign is going to become a plus sign because of the minus 9 that we put in here for C. And this becomes 4 times A, which is 4, times C, which is 9. And we're going to need the square root of that. And that's all divided by 2a, which in this case will be 8. Okay, so far we just got a whole bunch of numbers. Let's see. That's 16 plus or minus. Now 16 squared is negative 16 squared is 256. And 9 times 16, or 4 times, this is 36 times 4. That should be 144. That's right. Well, you can probably add these up in your head. You get 400. So that's where root's going to be pretty easy. So what we have here is, I can put it right here. 16 divided by 8, that's 2. Plus or minus the square root of 400 over 8, which is 20 over 8. Now, 20 over 8 is 2.5. 2 minus 2.5 is negative 0.5. And I don't think we're allowed to have, I don't think a negative 0.5 is going to work. I think we get totally messed up numbers if we go with negative 0.5. On the other hand, if we go with 2 plus 2.5, that'll be 4.5. That works out pretty good. That makes sense. If x is 4.5, then we have a right triangle. If we make x bigger than 4.5, well, here if the coefficients were the same all the way through, if this was a 6x and this is a 6x and this is a 6x, that might be kind of tough, because we're just multiplying everything through by the same number, except for we have different additions. But over here, I think the fact that we have smaller numbers in front of the x than we have over here, we can assume that this is the biggest. We already know this is the biggest length. So we can say that if x is less than 4.5, pardon me, if x is less than 4.5, these numbers will be smaller than this when we square them. If x is greater than 4.5, this will get bigger, and that means we'll have an obtuse triangle. So the actual answer, after all this, that you would come up with is x is greater than 4.5, which is 2 plus 20 over 8. You could try plugging in negative 0.5 in here, but you're just going to end up with a big mess. For one thing, up here that's not illegal, but this will give you minus 3 minus 1, which is minus 4. The length of the longest side cannot be minus 4. That would be the simplest way to throw out the minus 5 that you could potentially get down here. Now that you got 4.5, it's the only legitimate answer, then you can write this. A lot of calculations, but that's only because your quadratic formula uses a lot of stuff, doesn't it? It's not one of your simplest formulas. Well, this one shouldn't be too bad. What we have to do is show that we have a Pythagorean triple here with 6, 10, and DE. Well, how do we know that these two triangles are similar? If we knew that, and we knew that this was a right angle, we'd be done. But we don't really know that ABC is a right triangle. But how do we know that these two triangles are similar? After all, AB and DE are not parallel, so we can't use that. But how about the ratio of this side to this side is 2 over 3. The ratio of this side to this side is 2 over 3. and this is a vertical angle pair, which means we have our side angle side theorem. So these two triangles are similar. Now what we have to do is find the length of DE and see if this is satisfies the equations for a right angle. Or maybe I should say satisfies the converse of the Pythagorean theorem. So all we have to do is write DE over 12 equals 2/3. Or we got 3 times DE, oops, darn, DE equals 24, or DE is 8. Now if we put an 8 in here, do we have a right triangle? And let's see here. Remember our 3, 4, 5 rule? Well, 2 times 3 is 6. 2 times 4 is 8. 2 times 5 is 10. So we have a Pythagorean triple. The only thing we haven't figured out for sure is which one of these is the right angle. After all, proving you have a Pythagorean triple, or that these 3 sides satisfy the Pythagoras theorem, isn't enough to tell you which one of these is the right angle. However, the hypotenuse is always the longest one, and the right angle is the one opposite the hypotenuse, and vice versa. So this is the right angle because this is the longest side. It must be the hypotenuse. So first, you show that this is a right triangle, and then you show that this must be the right angle in the right triangle. Okay, well that's about it.